Audio Jungle. Audio Jungle.
Here we have a stream function. So basically, always remember this stream function is basically used to define 2D flow. Used to define 2D flow. That is one thing. And second thing, for this stream function, important part is it is always used to define for the incompressible fluid. Always remember, okay? Stream function is basically scalar quantity, all right? And it is used to define 2D flow. And in that 2D flow, one more important point is it is always used to define incompressible fluid or incompressible flow. Okay, so this 2 point you need to remember uh, for the stream function. So why we are going to use this stream function? First, you should know about the stream function. So stream function is, first of all, it's a scalar function. It's a scalar function. It's a scalar function. Second, it is, yeah. First point you need to remember about scalar function, stream function. It's a scalar function. Second point, it is used to define incompressible flow. Okay, it is used to define incompressible flow. And also you need to remember the stream function is what used to define incompressible flow as well as for 2D flow. It will not work for 3D flow. Okay, these points what I have written is a very important, and question they are asking based on this. Okay, all right. So now my point is stream function, first of all is scalar, second point is incompressible flow, and third is 3D flow. Now we'll start the definition, because this is the theory part related to stream function I have explained. Now mathematically how it is defined. Okay, mathematically how it is defined. So you just I just want to quote this statement. It is defined as the scalar function as the scalar function of space and time. I told last class also, space and time in the sense x, y, z, and time is also one dimension. So this function is what defined for the space and time. And in space we have 3 dimension x, y, z. So but it is valid only for 2D. Say any two axis we can take x, y, or we can take y, z, or we can take a z, x. Okay, like that you can take only 2 dimension you have to take. Okay, such that its derivative, its partial derivative. Okay, its partial derivative. Let me finish this 2 line statement, then I will mathematically I will show you how to understand this stream function. Its partial derivative with respect to time, with respect to any direction, with respect to any direction gives the velocity component at right angle. At right angle, it is denoted by Greek letter psi. It is denoted by psi, psi. Okay, psi. It is denoted by psi. Now this is the statement for this stream function. Mathematically how to understand? Like it is valid only for 2D flow, so we can take 2D flow. Okay, we can write 2D flow. This is now 2D flow. We can take, generally we are taking always x and y axis. So I must write here x and y axis. Okay. In x direction, we always represent x direction velocity component u, and in y direction velocity component is v. Okay. Last class also I had discussed, and everybody knows, because total velocity vector v, because for 2D velocity vector capital V, if you write, then it is ui plus vj. U is the component of velocity in x direction and v is the component of velocity in y direction. So in 2D you have to show this. Now how the stream function is what defined? So mathematically, just see. Mathematically, it is said, if you take partial derivative of a stream function in any direction, I am taking partial derivative of a stream function in any direction. What are the direction? X or y. So in any direction we can take derivative. Suppose I am taking derivative in x direction. So dou psi by dou x, okay, is equal to, it will give the velocity at right angle. So suppose I am taking derivative with respect to x, our x is here. So what is the right angle? Right angle is what here? This is the right angle, that is y, and in y direction what is the velocity? It's v. That's all. See the statement, what they said. It is defined as the scalar function of space and time such that its partial derivative with respect to any direction gives the velocity component at right angle. So I'm taking here the partial derivative of stream function with respect to x, and it will give velocity at right angle. So if I'm taking derivative with respect to x, so what is the right angle? It means you are reaching here, this is the right angle, and once you are reaching in this direction, what is the velocity? That is v. So we got dou psi by dou x is equal to velocity v, right? This is the one. Similarly we can write derivative with respect to y also. So similarly we can write dou psi by dou y, means the partial derivative of stream function with respect to y direction. So again, velocity you will get at right angle. What is the right angle now? Because you are taking derivative in y, you are taking derivative of stream function in y direction. So right angle means this will be right angle now here. This will be right angle. So once you are going to measure anti-clockwise angle, then it will be positive. And once you are going to measure clockwise angle, then it will be negative. This is very basic. No? If this is the I'm taking, this is suppose p vector and this is what q vector. If you are writing showing the angle, so angle if you are measuring anti-clockwise, so this will be positive, and at the same time if you are writing clockwise angle, it will be negative. This is very basic, you all know. So similarly, if you are taking the partial derivative of stream function with respect to y, means in this direction you are taking the partial derivative, so where you will get velocity? At right angle. At right angle means in x direction. So in x direction, what is the velocity? That is u. We write that. You will write here, but you are taking derivative in y direction, and right angle means you are going to x axis. So means you are moving in clockwise direction. So clockwise angle, you are measuring negative. So this will be minus u. Why we are not taking here a negative sign? Because we are taking derivative in x direction. Partial derivative of stream function we are taking in x direction, and we are getting velocity at right angle. So right angle, to get right angle velocity means we have to reach at y axis, that is the right angle, and from x to y if you are moving, then it is anti-clockwise, so it will be positive. So that's the reason this component we are getting positive. So it is now very clear, our stream function psi is nothing but stream function. So mathematically, hope you understood stream function. Mathematically, if you take derivative of stream function in x direction, you will get velocity in y direction, that is v. And similarly, if you take their partial derivative of stream function with respect to y direction, so you will get velocity in x direction with minus sign. Why minus sign? I have explained you, clockwise and anti-clockwise, right? So this is the mathematical model of stream function. But the story is what not end of here. This is for Cartesian coordinate. Once we are talking about the xy plane, or because it's a 2D, so xy plane or yz plane also you can write, or zx plane also you can write. Just like xy you have written, you can write for any two plane. Means you can write for any plane in the sense any two axis you can take. Just like here I have taken x and y axis, you can take x and z axis, you can take y and z axis also, but only two axis you have to take, because it is valid only for 2D flow. That is one thing. And if you are talking x y z, if you are talking about x y z axis, then this type of coordinate system called as a Cartesian coordinate. So whatever you have written here, Cartesian coordinate, whatever you have written here, the definition of stream function, it is for Cartesian coordinate. You need to remember, this is very special result. Okay, very special result. Similarly, we can write for the cylinder polar coordinate also. So once we talk about the polar coordinate, once we'll talk about the polar coordinate, means in polar coordinate always we talk about r and theta, r and theta. So for polar coordinate also we have to write the stream function. So here I can say, for the polar coordinate, see, this point is nothing but, so once you are talking about the polar coordinate, so r and theta you have to take. So I just want to show you r and theta. This is very special result. So here you can say r is nothing but radial distance. I can take this is r, which is nothing but radial r, and this angle is nothing but theta. Okay. So obviously two velocity component you will get, just like here in Cartesian coordinate you have velocity along x-axis and velocity along y-axis. Along y it was v, and along x it was u velocity. Similarly, we have to check in radial direction, we will have a radial velocity, that is vr, and in theta, which is the tangential, so in theta direction we'll get tangential velocity. Okay, always remember. So I can mention here. So this is suppose velocity v, resultant velocity is what, suppose v. So two component of this velocity will have, what are that? One is tangential velocity in angle in direction of theta, this will be the tangential velocity, and this will be the radial direction velocity, which is nothing but vr. Okay, vr and v theta, I must write here. Vr is nothing but radial velocity, and v theta is nothing but tangential velocity. Now again, if you are going to define the stream function, so what we will do, same thing, just like a Cartesian coordinate you have defined stream function. What you did for the stream function, if you take partial derivative of the stream function in direction of x, then you will get velocity in direction of y, which is nothing but v. Similarly, for the stream function derivative with respect to y, so you will get velocity in direction of x, that is u. So here also you have to take derivative of partial derivative with respect to theta and with respect to radial direction r. Suppose I am taking this partial derivative of stream function with respect to r, which is nothing but dou r, then what velocity you will get? You will get tangential velocity v theta. You will get tangential velocity with minus symbol. Just like a previous case, clockwise and anti-clockwise concept. Okay. Similarly, the partial derivative of stream function with respect to the angle d theta, we will get velocity in radial direction, which is vr. Now, one important point I just want to say, here I'm just giving the logic like how to write. This is the derivation. After derivation you will get, but as I told you, in GATE most of thing you have to uh, directly write, practice, you just write directly, because each and everything we cannot go for the derivation. But in fluid mechanics you might have seen the derivation for this, and derivation is hardly 2-3 pages, 2 pages derivation, but we can do. But here I'm just giving you the techniques like how to remember. Okay, just like here I have explained you like how to remember. So similarly, this radial also, radial velocity and tangential velocity also you make practice. Dou psi by dou r means if you are taking partial derivative of stream function in radial direction, then you will get velocity in tangential direction. Okay, and tangential direction velocity is nothing but v theta. Tangential direction velocity is nothing but v theta. Now coming to the radial direction, if you want radial direction velocity, then you have to take partial derivative of stream function in tangential direction, which is dou psi by dou theta. Always remember the unit of stream function is nothing but meter square per second. I'll explain you. Unit of stream function is nothing but meter square per second. To make a unit balance, this will take later also, I will explain this. So you have to multiply by r, radial distance. So this is now complete formula. 1 by r dou psi by dou theta is equal to v. Now you can check the unit. This is called the dimensional point of view. You can cross check this formula is correct or not. So 1 by r, which is r is nothing but radial distance meter, and stream function is nothing but meter square per second, and theta, it is unitless. Theta, we do not have any unit. So what will be the value here? 1 upon meter into meter square per second, which is meter per second. And check this VR is also meter per second. Means now this, once you multiply by 1 by r, then only your formula will be correct. So I am just giving you technique. Otherwise, this you can get the you can get result after doing the derivation also. But I would suggest don't go for the derivation. So this two formula, this is the polar coordinate and this is what the Cartesian coordinate, and both are very, very important. Okay, both are very, very important. So here I have explained stream function, both. This formula only you need to remember, okay, and we'll solve the gate problem also based on this. One is nothing but Cartesian coordinate, another is nothing but polar coordinate. Okay, in Cartesian coordinate you got that velocity, which was the u. You can say u is nothing but, just now you have written u is nothing but dou psi by dou y with minus sign, and v is nothing but dou psi by dou x. This is the one. Second, radial velocity you can write first. What is the radial velocity? So radial velocity, just now you have written, it is 1 upon r dou psi by dou theta, and v theta is nothing but dou psi by dou r. This formula you need to remember. Here I have written, you can write dou psi by dou y is equal to minus u, or you can write u is equal to minus dou psi by dou y, meaning is same. So this you need to remember. This is very important. Okay, we'll solve based on this. We'll solve the problem. Question they are asking based on this. GATE. This formula you need to remember. Already I have explained you why we are using the stream function, what is the purpose of the stream function, and what, with the help of a stream function, what we can get in result, and why we are using stream function. Everything I have written in first page also. If somebody asks to you what is the purpose of a stream function, so you have to say stream function purpose to study incompressible flow, to study 2D flow, two-dimensional flow. If you want to study, then you have to use stream function. All right. Now again, more and more analysis we have for the stream function. Some salient characteristics we have. So we'll do one by one. Now up to here we know this is the important key points of stream function. Key points of stream function psi. What are the key points? Just now listen, these all points are very, very important. Okay, number one, up to here it is very clear. This first point only I have explained you. It is valid only for 2D flow. It is valid only for 2D flow. First point, what you got, our stream function, since stream function psi is a function of any xy plane or yz plane or zx plane. For simplicity, I am just taking xy plane because it's 2D plane only. So xy plane will be 2D. xyz we cannot take because it will be 3D plane. Okay, so since y is the function of xy plane, I can say x and y, or xy plane. Okay, then how you can write? You can write a stream function psi is the function of x comma y. Now you have to follow all the steps. It's very important. Okay, and you will understand it's very easy only. So psi is the function of x and y. You can write x comma y. If I psi is now partial derivative, if I take if you check partially, it is depending on x and partially it is depending on y also. So what is the total derivative? If I want to write total derivative of d psi, this is called total derivative of stream function, then it will be dou psi by dou x, simple mathematics, into dx plus dou psi by dou y into dy. Okay, this is the mean of it. Now you need to check d psi. I can write what is dou psi by dou x. Just now here you have written dou psi by dou x is nothing but v. This is nothing but v into dx. What is dou psi by dou y? Just now you have written dou psi by dou y is nothing but minus u. So I can write minus u into dy, means v dx minus u dy. This is nothing but d psi, right? This is nothing but d psi. This is very important result. Okay, this is very important result. Now one very good outcome you are going to get here. Streamline, I had defined an equation of streamline for, we know, just listen carefully and just use this application. We know streamline, we know streamline equation for xy plane. What is the streamline equation for xy plane? It is nothing but dou u by dou x plus dou v by dou y. This is what continuity equation. This is the continuity equation for 2D flow and for incompressible flow. This is always remember this continuity equation, whatever you have written, it is continuity equation for 2D and incompressible flow. And as you have seen, our stream function is what only valid for incompressible flow. So now this continuity equation, which is 2D and incompressible flow, we can satisfy it with our stream function. Now what is the continuity equation we got here? So this continuity equation we got dou u by dou x dou v by dou y is equal to 0. Now we have dou by dou x. What is the u? See, we are going to satisfy it with the stream function. What is the u? Just now you have written u is nothing but stream function, check, u is nothing but minus dou psi by dou y. We just satisfied with that. Minus dou psi by dou y. Minus dou psi by dou y plus dou upon dou y. We have v. What is v? Dou psi by dou x is equal to 0. Now check this equation. It is dou square psi by dou x dou y minus plus dou square by psi dou y dou x is equal to 0. Or also once this equation also we can write dou square psi dou x dou y is equal to dou square psi dou y dou y. If this result is what indicating if stream function is what satisfying this equation, what is the mean of it? It's saying what stream function has satisfied? The stream function has satisfied continuity equation. This is what continuity equation. And once stream function is what satisfied continuity equation, so final result you will get like this. What is the conclusion of this? What is the mean of it? See, I will write the conclusion, so you just listen and always remember this. Okay, this is also very important because being a aerospace, you are going to write GATE also. So question very frequently they are asking. Okay, what is the conclusion of it? The conclusion is here, this result you got. When you got this result, when stream function, when stream function satisfied continuity equation. Continuity equation. Okay. Then what is the conclusion? What is the story behind this? What you have done for that? What you need to remember? So you need to remember existence of psi, existence of psi, which is nothing but a stream function. Existence of psi means a possible case of flow, means possible case of flow, possible case of fluid flow, better fluid flow. Doesn't matter, the flow may be rotational or irrotational. I will tell you what is the best thing you got here. Anytime when a stream function is what satisfying to the continuity equation, so this is the proof. Now stream function is what existing, so this is the proof. Now there is the possible case of fluid flow. If somebody asks you what is the mean of continuity equation, so if somewhere continuity equation is what satisfied, it means there is the possible case of flow. Continuity means what? The possible case of flow. If it becomes discontinued, then there is no possible case of flow, because that flow is what discontinue now. So if somebody asked you, so continuity equation from where, what is the source of continuity equation? It's a mass conservation. It's a mass conservation. The mass conservation, if you elaborate that, so outcome of mass conservation is the continuity equation. So if continuity equation is what satisfied, it means that flow is what continuous. That flow is what possible flow. Okay, possible case of the fluid flow. Mass is what conserved, means in a pipe, whatever the inlet is equal to outlet. That shows it is the continuous flow. And whatever the inlet mass flow is equal to outlet mass flow, if it is satisfied, it means its mass is what conserved. That is mass conservation. So anywhere once continuity equation will be satisfied, that means is the possible case of flow. Here if you check what you have done, simply this was the continuity equation, this was the continuity equation. You took this continuity equation and satisfied with the stream function, and once you satisfied, then you got this result. Once this result you got, then what is the conclusion? What is the point you got? The point is existence of stream function means possible case of fluid flow. Here it is clear there is the flow, possible flow. But what is the nature of the flow? It is rotational or irrotational, we don't know. To check rotationality, we have to go for another experiment. That is the next level. But till now, once stream function is what existed, it means there is the possible case of flow. And for that reason, whenever we are showing any flow x direction, y direction, we are using a stream function. Psi we are using. We are using psi. What is the psi? It is constant along the streamline. So for that reason, to show any flow pattern, we always use a streamline. Because along streamline, stream function psi is constant. And when psi is existing, it means there is the possible case of flow. Doesn't matter source flow, sink flow, rotational flow, irrotational flow, flow parallel to x-axis, flow parallel to y-axis, inclined flow, all the flow you have to show with the help of streamline only. That is the reason. Hope you got. Because if there is the streamline, it means there is the existence of flow. Why? Because along the streamline, stream function is what constant. And it says if stream function is what existing, it means there is the possible case of flow. Flow is possible. That's all. Right. Now, up to here, it is proved once size existed, it means there is the possible flow, but we do not know it is rotational or irrotational. So we have to check rotational and irrotational. Then what you will do? That is the next level. What you do for that? We have to write equation of angular motion for 2D plane, for XY plane. So we have to write next. This is, I think, fourth one. This is third. Now we'll go for the fourth one. What is the fourth point? We have to write angular velocity for 2D flow for xy plane. So what is the angular velocity now? The angular velocity will be, if you are talking about xy plane, so it should be along about z axis. On xy plane, what will be the angular velocity? Omega z. That I already have explained. Anybody can tell the equation of omega z? On xy plane, we have angular velocity, but that angular velocity will be about z axis. Hence, for xy plane, we have omega z angular velocity. For yz, we will have omega x angular velocity. Similarly, if you want to write zx plane, then we'll have omega y, means about y axis will have angular velocity omega y. So we are talking about xy plane, so we'll have omega z. Now tell me what is the omega z? It's a 1 by 2, right? 1 by 2. Here in denominator, after z, what will get? X. Then we'll get y. Opposite will be v and opposite will be u. This is the formula. Do you remember that? Do you remember that? This is the velocity. Yeah?
Yes, sir.
This is clear? Yeah? Yes or no?
Yes, sir.
Right. Now, so we'll satisfied with this again. So it is 1 by 2. We have dou by dou x. What is v? Now check what is the v. Again, you go back and check what is v in terms of psi. In terms of psi, what is v? V is nothing but dou psi by dou x. See here. So you just keep here. Nothing but dou psi by dou x. Check. Dou psi by dou x minus dou by dou y. U is nothing but minus dou psi by dou y. So it's nothing but 1 by 2 in bracket dou square psi by dou x square minus dou square psi by dou y square. Right? Dou square psi by dou y square. Right. This is nothing but omega z. Now we got omega z is equal to, which is angular velocity about z axis 1 by 2 in bracket, it is dou square psi by, I think, dou x square minus dou square psi by dou y square. Right? Now you should aware for irrotational velocity. This was explained nicely. For irrotational flow, what will be the omega z? For irrotational flow, what will be the omega z? It will be 0. So you keep here 0 is equal to 1 by 2 dou size dou square psi dou x square minus dou square psi by dou y square. Right? And it is, I think, here this was minus, this was minus, minus minus plus, sorry, you just correct it. Here we have minus, here we have minus, minus minus plus, so this is nothing but plus. Ultimately what you got, dou square psi by dou x square dou square psi by dou y square is equal to 0. This result what we have, this is the main outcome here. And if you have done mathematics, engineering mathematics in your engineering course, then you are aware with this equation. What is this called? Dou square psi by dou x square dou square psi by dou y square. If you aware, this is the value. If you take psi common, so what you will get? Dou square by dou x square plus dou square by dou y square. If you remember, this is nothing but grad square. Okay, it is called grad square vector operator. So you can write grad square psi. You can write, because this is the dot product, so you can take it this side. Now this value what you got here, see, this value is nothing but equal to 0. So this is nothing but 0. So ultimately what you got, grad square psi is equal to 0. Always remember, this is very special. And when you will get this, when the flow is what especially mentioned here, when the flow is what irrotational, then you got grad square psi is equal to 0. Okay, what is the conclusion of this? This equation, first of all, you always remember this is called Laplace equation. What it is called? Laplace equation for psi stream function. What is the conclusion? Conclusion you need to remember. What is the conclusion? Conclusion is if a stream function psi satisfied Laplace equation, it is possible case of irrotational flow. Because when you got this Laplace equation, when you took condition, what condition you took? For irrotational flow. So for irrotational flow, you have used omega z equal to 0, and then you got this Laplace equation. And once Laplace equation is what satisfied, it means it is irrotational flow. So once stream function is what satisfied continuity equation, it means there is the possible case of flow. Okay, once stream function is what satisfied continuity equation, then it is called possible case of flow. Here it is mentioned, it is possible case of flow. And once stream function is what satisfied Laplace equation, okay, once stream function is what satisfied Laplace equation, then it will be a rotational flow. That's all, done.